So hello everyone, and welcome to this presentation. So today we'll be looking at, as Peter introduced, this model on bias and confounding, which is practically one aspect under the umbrella of errors that are possible in research. I'll follow this outline where I'll give like a preamble and an introduction, and I'll highlight some of the key different aspects of the different forms of bias which exists in epidemiology and clinical research, including selection bias, information bias, and confounding. And my goal is for those who don't have any experience with these terminologies, to motivate them in such a way that they can help understand and anticipate these systematic errors in future epidemiological projects. And for those who have experience, to share some knowledge and also to do some review of some basic concepts. So one line I'll maybe open with is everybody use artificial intelligence in some form, so we know it works, but and honestly, sometimes most of the models, the people who even constructed the models, they don't know why it works. They are still looking for ways to explain why it works. So if something works and we don't really have like the first principles don't hold and we don't understand it very well, why should we really care about bias? But as we know, fundamentally in research, there are two like basic umbrellas of studies or study design. So we have experimental study designs, which are considered as the gold standard. And if we want to build any inferences on causality, this is primarily what we will have to do. But in several scenarios, it is impossible to like start an intervention for several reasons, for ethical reasons. So most of the times we still want to make some of these causal conclusion, even when we have observational studies. And because we don't really control our environment, like for experimental studies, then definitely we are liable to different forms of errors that will occur. And the aspect of causality has been experimented and evaluated by several people, like as from Bradford Hill. I will steal the thunder from the model of causality to talk a bit about this. So just about one of the most important, which is temporality, which kind of clears out the paradox of is there a chicken before the egg or the egg before the chicken? And also things like strength of association and specificity. And other people like Judea Pay has also explored causality from a different angle, like talking about the different ladders of causality, which starts from association. And there's this adage that association doesn't lead to causation. And once you get the association, now you can use intervention to kind of build on this to come up with causal inferences and counterfactual, which is kind of like you are looking at some form of minimal intervention you can perform. So let's say you are living in two parallel universes and you take treatment A in universe A and take treatment B in universe B, and then we try to see if there's an effect in that drug or not. So it's kind of to some extent a philosophical concept, but it's very important in building a causal inference. And one fundamental issue in research is that we are always limited by the resources we have, and we want to study some population, which basically is just some group of people who share some particular characteristics, which can be specific and fine-grained depending on the context. And because we are limited by these resources, we want to use just a small part of this population by pulling a sample from them. We conduct our study, and hopefully we want to ensure that our sample kind of measures what the reality or what is actually on ground. So that is the internal validity. And once we use this study, we can now move back to the population to see if our hypothesis can generalize to the source population This is fundamentally external validity. And once we commit ourselves to like using a sample from the population, there are different forms of research or of errors that that could arise. And the fundamental types of research of error in research is the random error, which we will not really focus on today. And then we have the systematic error. And systematic error is also called bias. And you have the different forms of bias, which is the selection bias, information bias, and confounding. And bias simply means like these are systematic errors in the study, design, and data analysis, and also data collection that will lead to incorrect estimate of not only association, but measure of absolute measures of disease, like the prevalence and the incidence of a particular outcome. And just to highlight here, because we have these fundamental types of errors in research, that is random error and bias. There's one which is kind of amenable to increasing the sample size, which is random error. But for bias, it is really problematic because regardless of what you do, even if you increase the sample size, it will not really change the magnitude of bias. So this is something which is very important, and we have to take care of it at every level of the research. And in terms of selection bias, this practically occurs like not when you have your distribution of the exposure and the outcomes in your selected sample, which are very different from what you have in the source population. And as I mentioned, bias occurs in different stages of your study. This could occur in the planning phase of your study. Particularly, one thing of importance is when we use non-probabilistic sampling methods to select our participants. And this could also arise when we have ambiguous inclusion and exclusion criteria. When in the course of conducting the studies, several issues could arise. This particularly for cohort studies where we have loss to follow up. If this is a significant issue and if the loss to follow up is related to the outcome or other important variables, this could lead to significant bias because at the end, what we have for the distribution of exposure and outcomes will not be similar to what is in the source population. And also diagnostic bias is some form of a specific type of selection bias in the sense that for people who have a risk factor, the way we investigate the disease for them is kind of very different compared to those who don't have the risk factors. And at the level of the analysis, which is what most of us do sometimes, is during analysis, we just maybe have missing data and we run an analysis on the missing data without really accounting for this. So at the end of the day, we do something called complete case analysis. By so doing, we exclude participants post data collection. And if we do this, then probably you have these discrepancies in distributions of exposure and outcomes in your sample and also compared to the source population, which will of course lead to bias. That being said about selection bias, the second type of bias is information bias. And unlike representation of the outcomes and exposure in the sample and the source population, this results from inaccurate assessment of the outcome and exposure variables in the study participants that you have at hand. So normally in a study, there's something called a ground truth, and you use several methods to ascertain if somebody has the disease, or you use different methods to ascertain if somebody has a particular outcome or not. And if in this case we consider the disease, then our method might accurately detect the disease, which in this case will be a true positive. And if the person doesn't have a disease, so in that case, that will be a true negative. So normally when conducting a study, we want to ensure that we maximize on the true positives and the true negatives and really limit the false negatives and the false positive. But when this is not the case, then we will have these discrepancies in how we classify participants as being diseased or not diseased. But this could also occur for like classifying people as being exposed or not exposed. And now, depending on the degree of classification, of misclassification of participants or classification of participants based on disease status or exposure status, we'll have something called differential misclassification or non-differential misclassification. It's just basically this simply means you just have a balance when you misclassify your participants. So a bit more on misclassification and non-differential misclassification. This typically occurs when you misclassify, when the misclassification is the same across the groups that you are comparing. And as I mentioned, misclassification is a concept that is not only for disease, but can also occur for the exposure. And most of the time you will have this like it bias towards the null value. So for example, if that factor was protective, then you will have more, the values will be closer to one if you have this form of bias. So we have this fictive example here where in reality the odds ratio is 2.67 for people who have who don't perform any physical activity compared to those who perform some physical activity. But now when you if we misclassify the physical activity status, we can see that the odds ratio has decreased a bit from the 2.67 that was initially the original or the ground truth, and it's going towards one. So it's kind of underestimating the actual effect size. And in the context of the differential misclassification, it's kind of like the misclassification is different in the groups to be compared. So for example, you misclassify the disease status maybe only for exposed people, or you misclassify the exposure status only for maybe diseased people. And this will most of the time lead to underestimation or overestimation, but unlike for non-differential misclassification where you have some form of bias towards the null, this is not the case. So it's kind of very unpredictable and it's difficult to determine. And normally when we go through literature, we see different names of bias. They come in different forms, but all of them fall under these two umbrellas as I've mentioned: selection and information bias. So some specific types of information bias. We have participant bias, which the most common is recall bias, very specific for case control studies. And then we have the interviewer or the observer bias, which could result from the expectation of the observer. And also we have reporting bias. So a bit on recall bias. This practically occurs when you have systemic differences in the way the subjects will report the exposure and outcomes. So I'll take a key example here. Most of the times, patients always, or diseased people always make an effort to kind of remember their exposure. So if you kind of perform a case control studies on children and birth defects, mothers with children who have birth defects will definitely try to remember more of the drugs they took during pregnancy than mothers for normal children. And of course, this will kind of decrease or underestimate or overestimate the true effect size. There are some ways to ameliorate this. So you want to use a control group that has a different disease. And most of the times, you want to carefully construct questionnaires that maximize the accuracy of completeness. And sometimes you don't want to really depend only on recall of the participants, but you want to go through maybe like electronic health records. If you have biomarkers in biobanks, you want to go through those to ascertain some of these exposures. On the other hand, as regards observer bias, this is when you have some form of, I would say, confirmation bias from the observer. So like the way they solicit the responses from cases and non-cases is very different. So let's say I'm conducting a study and I know physical exercise is related with cardiovascular disease, and I might have two people who are 50 years old, but there's one who has a cardiovascular outcome and there's another who doesn't have a cardiovascular outcome. For the person who has a cardiovascular outcome, the way I get the information about physical activity is practically very different. And in that way, maybe this will lead to some form of misclassification of exposure. And there are several ways to ameliorate this, of course. You use standard questionnaires and ensure that you have close-ended questions, because sometimes open-ended questions could lead to different arenas that you don't want to get to. And sometimes you also want to obtain the data from the participants and you verify them with the pre-existing records. You could also use biobanks. And I mean, one way to ensure that everything is consistent is to ensure that you have standard operating procedures to conduct interviews. And now this takes me to my third type of bias, which is called confounding. And this practically occurs when you have the distortion of the association between an exposure and an outcome. And this is most of the time due to an extraneous third variable, which is called a confounder. And sometimes this distortion can be so significant in such a way that it changes the direction of an effect. This distortion can also be there in such a way that it leads to some form of spurious correlation. Spurious correlation in the sense that between the exposure and your outcome, you have absolutely no relationship, but because the exposure is related to the confounder and the outcome is related to the confounder, as we'll see the criteria for that in the next couple of slides. You could have these kind of associations that will occur. And normally, once we have a specific research question using the PICO criteria or the PICO criteria, we clearly identify the exposure and the outcome, but most of the time it's always good in statistical analysis or along the course of the study to worry about the different third variables, or always keep it in mind that there is some third variable lurking in the background. And these third variables come with different names, and depending on the labels you attribute to these third variables, there are different ways to account for them. Why that is due in at the different phases of your study, that is planning, implementing your study, and also when you are doing some analysis. But the basic criteria for to define a confounding is that is this third variable that is associated with the exposure. It must not really be closer, it just has to be a correlation. And it kind of causes the outcome or is related to the outcome as well. But now it's not in the causal pathway of it's not in the causal pathway. And this description or this definition, I think it's been criticized now. People favor more of using directed acyclic graphs and a lot of literature research, because of course, if you want to ascertain that something is related to the exposure as well as the outcome, this is only based on what people have explored. And depending on how the confounding goes, you could have negative confounding as well as positive confounding. So negative confounding is just simply means it's kind of pulling the actual true effect towards the normal value, which in this case, if we take the odds ratio, relative ratio, or hazard ratio, it's 1. And for positive confounding, it's pulling it away from the null value. So if there's positive confounding, for example, with let's say cigarette smoking, and the third variable is cigarette smoking is the third variable, and we have cigarettes, we have alcohol as the exposure, and maybe lung cancer as the outcome. Then for positive confounding, we will have more like a higher odds ratio in that context if there's positive confounding. And if we have negative confounding in this scenario, then we'll have maybe a lower odds ratio. So I'll give here a basic example of confounding, which kind of like is this spurious correlation. So normally there is this concept I borrowed from this famous paper published in 1966, where they kind of explored the relationship between birth defects and birth order. But the third variable here was the maternal age. Normally, we are expected that it is expected that if you have more children, then you get older as you are getting more children, especially if those pregnancies are independent events. And ideally, it is shown that with increasing maternal age, you have increasing prevalence of or the incidence of these birth disorders. So once you have this kind of scenario, you kind of like put up your directed acyclic graph and check this condition. So the first condition is you check if the associated if this maternal age is associated with the exposure, which is the bed order. Of course, that is the case because you expect that at your fifth child you would have gotten or somebody is much more older compared to when they have their first child. And is maternal age related to Down syndrome? Of course, that has been proven. And this is not in the causal pathway. So this is a clear example of confounding, and which is totally confounded by maternal age because normally you find out that bed order is not really related to Down syndrome. So there are several ways to mitigate for confounding, and you can do this in the planning phase as well as the analysis stage. Unlike for information bias and selection bias, like once with those forms of bias, you only have to deal with them when you are planning your study and at the phase of implementation, because once you get to the analysis stage, that cannot be resolved. And in the planning stage, you do some form of randomization. Randomization is like you are kind of ensuring that you have an equal distribution of this confounding variable in the maybe in your treatment arms or in the different arms of your exposure. And you can do matching such that when you take a particular person who is exposed with maybe a third with a third variable, let's say for age, you match those people for the age group. Of course, this they have their different challenges, because for something like matching, if you select several variables to do matching, and then you have very severe restrictions on the sample size. And one third way of doing or mitigating confounding is you kind of restrict. If you know that something is a third variable, you just restrict everybody to one particular group, and then you study just that particular group. Of course, this will have impact on how you can generalize your results, because if you study just people who are between the age of 45 to 50 years, then you can only make inferences on those people when you want to generalize your study. And on the other spectrum of this, like during the analysis phase, you do there are different things you can do, like stratification. So you do analysis at different levels of your third variable. You do some form of standardization, and most of the time standardization is a method which is mostly used to kind of measure the burden of disease. So it's kind of comparing the adjusted rates of the disease under the assumption that like the distribution of the confounders is the same. Another method that is frequently used is multiple regression, such that you could adjust for other variables. And the advantage of this is that you don't adjust only for one third variable, but you could adjust for several third variables as well. And most of the times, of course, this is not an ironclad rule, but there's this 10%, 10 to 15% rule of confounding, where you take like the crude measure of association. In this scenario, I used the relative risk as as the measure of association. So once you get the absolute percentage change, if it is more than 10%, then you can start thinking about looking at other criteria to see if you have confounding or not. But I just want to highlight that confounding is more of is a causal concept, and it's not something that can really be evaluated by just statistical methods. So there's this also, this is more is of a supplement to the 10% rule, which is like a general guideline. So normally, if I really have my people criteria set down and I have, for example, a third variable, then first thing I do is I'll do some form of stratification. I do a crude analysis. So when I don't consider the third variable, and then subsequently I do my stratification. With this stratification, I kind of look at my effect size for the different for each strata, and I check if these are the same or not. So if these are not the same, of course, you have to check this using different statistical tests, but not to get into those details. But if these are the same, then you know that there is no effect modification. Effect modification is something else, so I will not really get much into that. I think there's a module for this. But if you have the effect, if you have the effect, if you have the effect across the different strata, which are very different, you conclude an effect modification and then you report the stratum specific estimate. We'll see this, I think, in the next coming weeks. Once you have now the estimates that are kind of similar, then you have to check the 10% rule, 10 to 15% rule to see if you have to check the 10% rule by calculating an adjusted estimate. An adjusted estimate now accounting for this your third variable, and check and see if they are different. If they are different, of course, then you have some form of confounding depending on the criteria. And if they are not different, then you have a scenario of no confounding. But I just want to highlight that confounding is more of something which comes from the population and not just from a particular sample that you get. So I have this toy example here where I'm looking at the relative risk between for people who are physically active and development of coronary heart disease. So I have the broad population and then I stratify them into two. So less than 45 and greater than and 45 years or older. So the crude relative risk here, we see that it's like a 43% decrease in the risk. But when I look at it for the different age group, they are pretty similar. So when I have this scenario now, I cannot conclude that I really have an effect modification. Of course, this has to be tested by different statistical tests. So once I get this now, what I do is that I calculate the adjusted, which is the adjusted relative risk is 0.84 compared to the 0.57 for the crude. I see that there's like the absolute difference is like 32%. So I will conclude that this is a confounder. And then what I will do in my presentation is that I present the adjusted threshold, which means that I kind of cancel out the effect of this third variable and getting the effect of or getting something which is closer to the true effect. So I have these are some references. I will not really, what I can conclude is that bias is not something like a black and white problem, especially in observational studies, because there is always some gradient or some degree of bias which has to be acknowledged, of course. And there's different forms of or the three different types of bias that can occur in research. A selection bias, which results from unrepresentative sample in the sense that the distribution of your exposures and the outcomes is not representative of what you find in your target or the source population. And then information bias will result from inaccurate assessment of the exposure and cases. And then the confounding is when you have this third variable or this third looking variable that kind of leads to spurious correlation. And one thing is, if you don't really take care of selection bias and information bias during the implementation and the planning of your study, no statistical method will really get you out of that. So for confounding across the whole spectrum of across the different time spans of your study or your project, you'll be able to account for that. But regardless, although confounding, you can solve that during the analytical phase. It's good like to start addressing all of these things when you start planning your study. Thank you.